Hello and welcome to Explaining Rust Analyzer video series, where we try to understand how Rust Analyzer works one subsystem at a time. So, last time we looked at how syntax trees look like in Rust Analyzer. Specifically, we walked through API walkthrough test and saw how you can actually use syntax trees and the API we have in Rust Analyzer. Today we will start looking into the implementation. The implementation lives in a separate crate called Rowan. So originally I planned to just dive straight into the code, but looking into that I understand that it's kind of like probably premature at this point because well, syntax trees are one of my favorite topics, and this is the part of Rust Analyzer I've polished more than any other part, and sadly that is why they're like horribly complicated. They're like very complex data structures. There is a lot of unsafe, and the actual API is actually very tricky inside. So I decided that rather than looking at a real implementation today, we would rather just implement a toy implementation of Rust Analyzer syntax tree from scratch. The goal here is to understand the programming model and how the underlying data structure works, and then next time we will actually look how we can optimize this toy implementation to be more memory efficient, more time efficient, and have extra features. So let's start. First of all, I must say that the implementation of syntax trees we use is pretty fancy and it's nothing new. Originally, this idea was implemented in Roslyn, and again, I'm not sure if Roslyn folks were the ones who invented this representation or if they just used it from some other source. And actually, it's probably not like completely innovative, because if you like squint hard enough, what we are going to discuss is basically functional zippers, if you know that, but unrelated. Anyway, originally, the representation we will be looking at today was implemented for the Roslyn compiler for C#. It is somewhat documented in Roslyn, but the documentation there is like pretty scarce. That implementation inspired the implementation of lib syntax in Swift, and actually that is very abundantly documented. And that is like the main documentation about Rust Analyzer syntax trees said this. So let's go to the Apple Swift and find here syntax readme. Okay. So this document describes the new Swift syntax tree library. I'm not actually sure if they've integrated this into the compiler or not, because as usual, as always happens with IDEs, Swift had this like command line compiler with like very specific IST, and then they realized that, hey, we cannot actually use this IST in IDE because IDE requirements are different, and then they wrote like this lib syntax thing, which is separate. And I'm not sure if they are actually using that in the compiler, or if the compiler still uses like the old IST. Anyway, this is a very like long document and very thorough, and it even has like this picture, and just staring at this picture you can like understand everything. But we are not going to read it. We will just implement some parts of it. And yeah, I must say that although Rowan is like very inspired by this specific document, some specific design decisions are different and actually somewhat more fancy. We will look into that later. And yeah, just for completeness, here's the actual syntax tree library used by Rust Analyzer. It lives in Rust Analyzer Rowan. So okay, let's start implementing. And let's call it mini Rowan. And yeah, the reason why it is called Rowan is that the original idea used red and green in the description, basically, the syntax tree is a composition of two trees, a red tree and a green tree. And I was thinking about like what kind of thing is like a tree and is red and green, and figured out that Rowan it is. Okay, so let's start with describing what we even want from our tree. I can't spell. No, I can't spell. That's the horrible issue with my work environment. Spell checking in VS Code is like horribly slow, horribly inefficient, and I'm like waiting for years until someone makes it like fast enough and not annoying enough. Okay, so first we want the tree to be full fidelity, meaning that whitespace and comments are part of the tree. Then we want the tree to be, I don't know, let's call it resilient and semi-structured. And that means that we can represent arbitrary invalid code. To give an example, if I type something like this like obviously isn't valid Rust, because like functions should have a name, a list of parameters, a body. But if we actually look at the syntax tree, we see that in the syntax tree we actually do have a function node, and pub create correctly is parsed as visibility. And like if we add a name here, it will be correctly parsed as a name of a function. So this tree correctly represents completely invalid code. We also want the tree to be a value type, meaning that the syntax tree contains exactly the same information as the underlying string, and that it doesn't have any identity, any position in the project, and that you can like compare them for quality. Basically, you like when you work with traditional compiler, you often want to assign identity to trees, so that you say like, hey, like this is a particular expression which lives at a particular offset in a particular file, and it has a certain type, a certain value, that sort of stuff. That works great in compilers because the tree is static. So if you have a tree, it doesn't move, it just sits there. For RDs, this doesn't work that great because you want to do refactors. And when you are refactoring, when you're implementing refactorings, you need to manipulate syntax trees. And when you start to transform things, start to duplicate functions or move expressions from one node to another node, you kind of lose this strict sense of identity. And that's why we want to treat syntax tree as just a value type. We also want it to be immutable. And that's just for our sanity. Again, in the compiler, which is organized in a strict pipeline, it's actually is okay to mutate syntax tree in place and to just like desugar it in place or something like that. In IDE, well, you simply cannot mutate syntax tree because the only truth is whatever user has written. And even if you want to do some simplification, that like desugaring if too much or if left too much, it doesn't really help you because, well, you can use this desugaring to, say, compute types more easily. But then, if you need to apply some kind of an assist or a fix, you cannot apply it to desugared state. You still have to have original ISD. So yeah, now we want trees to be immutable. That said, we want trees to be cheaply updatable. And that's interesting. So although the tree is immutable, there are at least two separate cases where you might want to compute a different tree. First use case is during refactors. Most of the refactors are local. Although you have a syntax tree for the whole file, usually you want to not rewrite the file completely, but just to modify several chunks in the file. So for example, if we have function main and we have a collections hash map here, we have this replace qualified path with use assist, which inserts a use at the beginning and shortens all the paths here. So this is the kind of like prototypical assist in that it doesn't really change file that much, but it does change a whole bunch of different strings in a file, because if there are like several usages, then all of them will be shortened. So we need cheaply update for refactors. And the second case is incremental parsing. User usually types in just a single place. It would be cool if the syntax tree allowed cheap in-place updates. Note that we don't actually we do implement incremental reparsing in Rust Analyzer, and it is fully supported by both the parser and the syntax tree, but we don't actually use it in production because it turns out that parsing isn't just a bottleneck for stuff that IDE typically do. But still, it would be nice that if the syntax tree library provided for that. And I want to add a star here. And the star here is that although I originally started design Rowan with this requirement, and for this requirement the design seems okay, I'm actually today not so sure that that is the best design. That is because although sometimes you do need to modify trees, most of the trees are actually read-only and immutable, like fully immutable, not only like in a sense that if you want to refactor them, you need to send a diff to the client instead of refactoring them in place. But immutable in a sense that you are never actually going to modify any or refactor any files in standard library. So in this sense, I think a better representation, which is not implemented in Rowan yet, is actually to make it possible for a syntax tree to be backed by two different representations. One representation is a very compact, very space-efficient, dense array, which is used for read-only trees, and another is a data structure which we'll be implementing today, which is like more like your usual tree with separately allocated nodes, which is cheaper to update. Anything else I want to say here? Yeah, nothing. Then I actually want the tree to be conveniently updatable. And that means that although the syntax, we want to treat syntax tree as an immutable value, we do want to be able to conveniently write refactors using the terminology like remove this node, replace that node with this new node, and those kinds of things. And actually, implementing convenient API for updating trees is very hard, and it's like one of the most elaborate bits of the Rowan API. So we won't be looking at this in this series of lectures. For like refactoring API, I guess we will need a whole separate topic. But still, it's like a nice requirement. Have I forgot something? Full fidelity, resilient, value type immutable. Yes, I forget one very crucial thing. That is easy to navigate. Specifically, we want to go from node to its children, which is easy, and also parent and siblings. And those two are actually hard. And actually, let's merge this too. And actually, like these two requirements are those requirements which made syntax tree complicated. We want it to both be immutable value type and we want it to be easy to navigate. Okay, so let's start coding. And we actually start with like resilient and full fidelity requirements. And if you think about those requirements, they basically mean that your syntax tree should be able to represent arbitrary soup of tokens. So while in traditional compiler, you might want to have like struct, which has a name and a list of fields. In IDE, you actually like have to deal with arbitrary stuff happening here. And you notice that like I've typed like complete garbage there, and still in the syntax tree we recognize like things like fields. We like explicitly represent error nodes, and we still correctly represent the whole thing as a struct. So we cannot just easily use a fixed set of fields to describe an IST node. We really need to be able to store arbitrary data there. And that's why there is like this first idea. We will actually use dynamically typed tree. And we should take this in quotes because it's not really about like Dean or any. But basically the idea is that we won't try to enforce any types in the tree. We say that the tree is a homogeneous tree of nodes. That is, all nodes in the tree have the same type. Let's actually start. And like the primary attribute of a node would be so-called syntax kind. So syntax kind will describe like what kind of token or internal node this thing is. And we will have, for example, like const, let's say fn, will be syntax kind 1, and that's like the whole fn node. The fn token will be like syntax kind 2, and then function will also have a name. So that would be syntax kind 3, and the name will have ident token 4, and then we will have a list of the parameters, and that will be 5, and etc. etc. So let's I guess we'll be using this for some examples, so let's move it there. By the way, quick Rust tip: place module declarations before use declarations. That's kind of much more readable, because when you want to re-export stuff from modules, you won't have to figure out whether module or use goes first, because well, modules always go first. Okay, so that's like the syntax kind. And then we will have token, And token is a thing which represents a diff node in the tree. And the token will contain just kind and text. Let's actually try to provide some better API here. Interesting. So I wonder if our getter assist understands that if the type is copy, you shouldn't return a reference. No, that's actually like something which you can fix. Basically, change this generate getter assist such that if the type is copy, then we don't need this reference. And I'm killing documentation because it's not useful, and I want this to be rather compact. Okay. Yeah, and by the way, for the string, the assist actually correctly returned not the string, but $str, which makes more sense. Okay, then we will have internal nodes. Internal nodes will also have a kind, and we will have children. Children. And node can contain as a child a node token, so we will also need a struct something like this. And I also want to store len here. We need a getter. And for the length field, we just return len. And we also want to have children. Not sure what's, yeah, let's just keep this simple. So I've made node.token generic such that we can use the same enum to return either an out value or reference, or as we will see in the future, a red node or green node. Okay, so this is starting to shape up, and yes, we can say that we have constructor function here. And we don't actually need the length because I need to change this. I really don't like using like self in return methods, and like when you write record literals because it creates more work for the reader. When you're reading code, when you're seeing self, you need to mentally like resolve this self to an actual type. It seems like it's not hard for the compiler, but it's hard for the human. It seems easier to just like always spell the type here. So lan would be children, iter map int text lan, and we want to send this to users, I guess that will be inferred. And yeah, we need to import text10 here. Okay, so this is starting to shape up. Also, let me. I don't really like that. By default, RustFMT really likes to spread out stuff over many lines. Like, it's true that when you do a lot of lines, it helps with reviewing the diffs because the diffs are smaller. But most of the time, I'm not reading diffs. I'm reading actual code. And when I'm reading actual code, I actually personally find it's more readable when the code is more dense. Like, I like when the code is sparse in terms of functionality, not a lot of like different things happen on the same line, but at the same time dense in terms of like actually like using the space. So let me copy. Yep, a config we used in Rust Lighter, which is just this thing, and yeah. So yeah, that's your typical immutable syntax tree, which supports iteration, but only downward. So we don't support upwards iteration here. And what's interesting is that this tree also supports cheap updates. So I'm not sure what's the best API here, but for example, we can say something like oh, it doesn't support cheap updates right now, but we can make it so. Okay. So we'll support ReplaceChild method, which takes an index. The new child and returns a new node. And the way this will work is that we will have yes, and yeah, that's yeah. I guess we will be discussing editing APIs somewhat later because the idea here is that if you have like this tree and you want to mutate a single node inside of it, you can create a copy of a tree with structural sharing by only modifying the path from the current node to root. However, we do not currently have the API to talk about the root of a tree because we can only talk about a single node. And this single node points to like a specific node inside the tree. So we like cannot implement this respawning strategy here. But actually, no, actually I think we can do something like this. So we cannot do respawning, but we still can modify a single node by keeping structural sharing. So what we want to do here is that we want to say, how would I do it here? Okay, so so children take I want to take this many children from the start, and then I want all of them cloned. Then I want to chain it runs new child, and I see the chain is red because cloned does not return an iterator because our node isn't actually clone. So let's derive clone, and let's derive. By the way, the fact that this suggests copy is a bug because we know that copy isn't applicable here because some of the types of the fields are not copy. So yeah, this is a bug. Please fix it. Okay, and this also should be derive clone, and that actually can be clone copy because it's generic. And then we want to chain self children skip drop. This is called skip. Oh, okay, I'm forgetting. Yeah, it's funny when you write an IDE and like initially when it doesn't complete you something, you usually blame the IDE because the IDE is buggy, but once IDE is complete enough, it usually turns out that like your code is buggy. And I'm kind of like still, and like today, it's like true most of the time that like if Rust doesn't complete something, that like your code is wrong, but I'm still not used to it and I like feel like what might be the bug in the IDE. Anyway, we want to skip this node which we actually replacing, and then let's also assert like that. Yeah, something like this. And we want to actually collect this. I wonder why it doesn't suggest me to collect this because it should. Okay, because I'm not calling collect. Yeah, again, it's not a bug in an IDE. It's like bug in my code. I haven't called collect. So yeah, we calling collect, and we can collect this to a vector children. Okay, and then we can return node new self kind children. Or actually made kind. Yes, kind is copy. No, not self children, new children. Yeah. So this method replaces a single child in the node with a different child. And to do it, it needs to clone all other children here and there. It's probably could be refactored a little bit better. Children to the, let's call that children. And this will be right children. And yes, and like left children, chain new child, chain right children. Okay. So yeah, we return a new node modifying a single child. The problem here is that these clone calls are complicated because are costly because of the way this is implemented today. They will do a deep clone of the whole subtree, so this operation isn't really fast. And to make it so, we actually need to make this stuff using structural sharing via references, via reference counting. So let's call that this is now token data. And token is just an arc of token data. You actually don't want to keep this cloned. And similarly, this now begins node data. And node is just arc of token data. No, node is arc of node data. Okay, this now is node data. Again, that's kind of like the case where using self would actually helped, but I'd rather like replace this manually or with some ID feature. Than have to read this self every time. And similarly for token, this actually is implementation on token data. Yep, now it should compile actually. Let's try component. Oh, wow. I think I've written like a whole bunch of Rust, almost 100 lines, and it compiled from the first try without any borrow checker errors. That's achievement. Okay, so now we get this. Again, this shouldn't be cloned. Now we have this immutable tree, which, well, is a mutable value type, which allows us to represent trees with full fidelity because we can just have tokens for whitespace, and which allows us to represent arbitrarily broken syntax because we do not try to enforce type or structure in the tree. It's just an immutable homogeneous tree. The problem here, though, is that this tree is, yeah, actually, let's try to implement some smoke tests. So let's represent like tree like this. So we have we'll probably need some more kinds here. Let's make all this pub just to get rid of errors. So before this line, this will be nodes. Here will be tokens. And for our example, we also need, let's start. Yeah, I'm wondering what would be like the less annoying numbering scheme here. Because in real Rust analyzer, like syntax kinds are assigned by code generator, so we don't have to adjust them manually. But here we do this manually, so we need to invent something like not horrible. Okay, so we also need token number. Let's call it even int. And we need token operator. No, let's call the token plus. When writing IDs, I found that it's useful to, like, it's less confusing to name the tokens by the name of the symbol they represent rather by the name of operation. So it's like not binary operator plus, it's just a plus sign. Because then if you use plus somewhere else where it isn't a binary operator, like for example in trade bounds, like using like this addition say token would be confusing. While plus is just like the name of a glyph. It's better. And here we should have pubconst being export. So here, one would be... I wonder if those new methods should return. Yeah, let's... I wonder... So what I'm thinking about is like, should we like automatically wrap this into an arc? And I think we probably should, but I wonder if I can write this impl. Probably not. Yeah, sadly, coherence rules are against me. Okay, so let's do this just in a stupid way without like trying to be clever. So kinds int no, let's actually do like properly like this. Then we also need kind Whitespace. Okay, so before 100 will be like special tokens like Whitespace and the error token. Okay, 1. This will be 2. And then we will have plus. And then the addition node will be so kinds in expert and the children okay 1 into OS clone into plus into OS into and 2 into. Okay. And to make this work, we also need derive debug here, here. No, actually, yeah, let's just go with derived because like derived representation for trees would be like pretty inconvenient, so we will have to write better one at some point. And we also need to implement. Actually, I wonder if I can cheat here. Okay, yeah. Here we will exploit a bug from an IDE because it doesn't actually know that such generic impulse wouldn't work, but we can still use that to write a scaffold. Okay, so let's run the smoke test. And it works, and yeah, we kind of like get a tree. And you might have noticed one very interesting thing here is that we actually reuse Whitespace token here. In that the tree actually, and this represents 1 plus 2. And this is actually cool because we can have structural sharing. And in particular, let's say that our original syntax was structured like this, because our tree is purely functional and doesn't have any identity. When we want to represent outer addition, we can actually do something like this. And yeah, I don't have parentheses here because yeah, that would require like us to like more code, but like imagine that parentheses are there. So let's call it this is addition, and then we represent multiplication like this. Can be an expert, and here we want to have, okay, let's actually try to keep this more compact. And yes, like the problem here is that when you want to like work with syntax tree completely by hand, that gets pretty unwieldy very quickly because they have a lot of tokens. So you really need to build some higher level infrastructure to manipulate the whole set of tokens of trees at the same time. Okay, yeah, and that's cool. Now this multiplication node represents this syntax tree, but I guess I can make this better by saying that this one is actually multiplication and this is using star, and this one now is actually addition, and what we represent is this tree. So like now we don't need parentheses, and now I start hating the absence of whitespace here. It's like completely relevant to what I'm trying to tell to you, and it's really not using your time in the best possible way, but I just like cannot stand that it's like not correct. Okay, so now this is like pedantically correct and pedantically doesn't compile. So we need to go along here. It's one of the places where I would not be against some kind of an auto clone feature. On the other hand, it's actually good that we get an error for plus because we should change it to error for star because we should change it to plus. Anyway, this is really, really cool. Now, this addition represents this syntax tree. But it uses it more efficiently than a naive implementation because it actually shares the data for these subtrees. And actually, while we are at it, let's do, where is no data? Let's do impl. Let's actually implement displays for those things because they actually have a very specific display implementation. Token data. And here it is simple. It's just we should just show text to formatter. And here it is slightly more difficult. We need to say for child in children. We need to display this child into parameter and return an awk result. And I guess this also needs, yeah. At some point we will add alias for this download token. Okay, can we now just print it and get back the original? Yes, perfect, it works. So yeah, we see that the tree indeed is a full fidelity representation of the source code. So that's nice. What is less nice is that the tree is inconvenient to use. It's inconvenient to navigate from the tree, through the tree. And that is because we do not have parentings. If we point at, say, this one, we cannot like go from it to the multiplication, to the addition. We can only go to children because this is a token. It actually doesn't have any children. So let's now implement navigation. And for that, we'll actually move what we've just implemented into the green module, because we actually implemented green tree from that document I was talking about. Okay, so we need to probably move all of this into green. Okay, let's use this and this and this. Token node token. I'm trying to like arrange them into the single order. Okay, that sounds reasonable, and let's use token data, node data. Now the test should still pass. No, it doesn't pass because we don't need this import here, but we actually need an import here. And now rest passes. Okay, let's squash the unused warnings. Okay, so now then we have green nodes. Let's actually rename everything to green token, green token data, green node, and green node data. Perfect. Okay. Let's see if rename works correctly. Yes, Yai automated renames. Like renaming this manually would be pretty painful. Well, not excruciatingly painful, but still. But automated rename got our back. Okay. So now let's try to implement red trees. And the goal here, actually two goals, but they are like basically equivalent. We want to implement parent, and we want to implement text range. Remember that in the green node, we only have text length. Actually, let's not call it range. Let's just call text offset. In the green node, we only know the length of the node itself, but we do not know its relative position in the syntax tree. For the red nodes, we actually want to get the offset of the node from the start of the syntax tree. Like for, where do we have a test here? Yes. For this one, the offset will be 8 selected, so the offset will be 8 for this one, and the length will be 1. And the offset for this one will be 0. So although these ones are actually represented by the same syntax node, syntax token, because yeah, there's structural sharing, we want them to be different by the offset. And that's tricky, and that's like the core idea of like these zippers or red nodes or cursors, how I call them in Rowan. So we have red node. No, we will have red node data. And we will have red node. And the red node would actually be just a reference count and pointer to the red node data. That sounds very familiar. And red node data will contain corresponding green node. But it will also contain a parent. And that's, oh, and it will also remember the offset. Text offset. So yeah, that's actually like very simple. We want kind of like to enhance our green nodes to have parent and text offset. Offset or offset. So we just add those two fields. But this is actually really interesting. So if you look at the green node, then the green node stores reference counted pointers to child nodes, while for red nodes we actually do exactly the reverse. We store reference counted pointers to parents. Let's write some. And yeah, and the idea here is that we will have one-to-one correspondence between red nodes and green nodes. So every red node, every green node in, well, sorry, not exactly one-to-one correspondence because we have structural sharing. So I'm getting excited because it's like really fancy thing. So we want to store one red node for each syntax node in the original file where they are not deduplicated. And each red node will store a corresponding green node. Okay, let's go back to our red nodes. So let's start implementing this. First, we will have actually just duplicating green node API. Oh, by the way, no, let's put this on pause. I want to do a little refactoring here. In the green node, I actually want to say, do we also have pub type green element, which is node token, green node, green token. Yeah, and now okay, yes, now I actually don't have to like repeatedly repeat all those like green token, green like node token, node token, which was stupid and which probably left you wondering like why the hell he's doing that. Okay. Let's actually do the same for tokens. Yeah, and here, like rather than using like Smart IDE, we just use multiple cursors, which yeah, gets the job done sometime. Okay, and finally we have red element, which is not a token. Red node, red token, and those are actually also clone things. Okay. So the main thing this thing has is actually access to green node. And I don't think it needs to be public, so let's just yeah, let's let children for later. So we have this, and we also have okay. That was the token. I'm writing an impl for node, so here. So these two methods were actually impossible for green nodes, but for red nodes, they work okay. Okay, so let's implement the constructor. We will take green node, and this should be the root of our tree. So we will return RC new. Here I think I need to wrap this on RC, but maybe not, we'll see. Okay, and here I want to have red node data. Oh wow. Seems like that's a new feature in Rationalizer. I think that it was merged only today or like a couple of days ago. Now completion for structs can actually pre-fill all the structs, all the struct fields. Not sure if we really need this because like the way I usually do this is just like type these and then you can just like alt enter and fill those fields. But anyway. Oh, right. Parent is actually optional. So we want to do this. So the root node doesn't have a parent. Its text offset is 0, and its green node is just root. And let's implement this for tokens as well. So yeah, I like impulse and I like that structs are when structs are at the start of a file and then impulse, and impulse should be in the same order as structs. So we parent shouldn't be red token, it should be red node. Yeah, that is when multiple cursors fail you. And we will actually always require that tokens have their parents or not. Yeah, let's make a parent type optional. It's not really required. And this one we actually want to keep private, I think, for now. And we want to return red token. So we want to return red token data wrapped in RC new. And we will be using the provided parent, the provided text offset, and the provided green node. Actually, yeah, I think if this is going to be private and we are just like setting all the fields, we don't really need it. We do need this though. And we also need green. Actually, I now realize that probably separating nodes and tokens into different structs isn't the best idea because it isn't, well, it's a good idea for rationalizer because I think it's important that you can differentiate between tokens and internal nodes, but for like just typing a toy version of mini Rowan that just duplicates the whole code, we should have gone with just like unitype node, where the token would be a node which doesn't have children. But anyway, let's continue with this. That is where like some upfront planning can save you a lot of work. Okay, now this all works. And then it compiles, and textlan, this should be textlan. And this should also be textlan. And we probably want text offset and textlan be together. Okay. And we also want to re-export all that stuff. So let's say that we have red, and yeah, kind of like you might be feeling that this is all an exercise in duplication because like we have tokens and nodes which are the same, and we have like green and red which are the same, and that's, you wouldn't be entirely wrong. It's a lot of duplication, but I kind of like that this duplication is encapsulated in like one crate, which is very basic, which has few dependencies, and which is like very dependable by the rest of the Rust analyzer. In general, in Rust analyzer there's like a lot of code which is just duplicated, but usually this code is in the places which change rarely, and that's like something you write once and never feel the pain of duplication. So the duplicated code is only harmful if you also need to change it, because then you have to change every duplicate. Okay, and now comes the magic methods. It's like also like the slightly uncomfortable moment for me because maybe I forgot to like some crucial moment, crucial thing, and I won't be actually be able to write it. But let me try. So method to get the children. Children. And this will this time this won't be able to return a reference because we only have access to green children, but we want red children. So we will have to return an iterator where item is red element. And you probably want to borrow from the current node for the time being. I don't know. Okay. And the way we do this is that we take our green node and we take its children and we iterate them. No, let's. I'm wondering if I should change this to iterator or not, but yeah, let's not do it right now. Especially not while we are writing some other thing. And I want to map each green child to what? I want to match of a green child. And if it is a node, I want to return a new red node. What's that? RC. What happened? So yeah, okay, yeah, because it's like red node data. Because red node is RC, and when I try to fill fields of RC, I obviously get to like fields of a private struct, which is a backend ID. It shouldn't be suggesting fill struct fields for structs from outside of your crate anyway. So the parent is actually now some, and it's some self clone. Actually, let's write this way. A text offset. Text offset is text offset of a parent plus the sum of all text offsets of the siblings which were before this node. And we can actually compute the sum on the go. So let's say let's move text offset. Now let's call it offset in parent. And it starts with 0. So text offsets is text offset of a parent plus offset of child and parent. And then offset in parent gets incremented by, actually we can reuse this for both branches, so we can pull this up. And offset in parents gets incremented by green child text time. Okay, so now this is like text offset, and green is clone node. And we do the same thing for token. Okay, and I actually feel that this might be it. Okay, let's also write an impl for red element. Yeah, that's another annoying bit. You don't get completion here for like really stupid interaction in VS Code between snippets and completion, and we should fix this someday. Like it worked, and then we made snippet completion better, and that broke the completion here. So yeah, too bad. Syntax element and all those things. Let's write one and then copy paste it. Yeah. So this should be text offset, this should be text and this should be parent. Okay, now it doesn't compile, so okay, yeah, we really are programming Rust. So why is this happening? Okay, yeah, because the types here would actually be different, so oh, wow, there's like a lot of mistakes. First of all, we actually need to convert this into red elements, and then here we actually want to return a token. It's interesting that like, no. Anyway, so let's let's get some more source for copy paste. Okay, now it should compile better, hopefully. Ah, missed one. And this all should be public. And why is that? Because, oh. Yeah, and that's that embarrassing moment. So actually, can I just, well, that's like, can I just like write this? We now have arbitrary self types, so this might just work. Parent is option of red node and self is a red node. So when cloning it, we should be getting a red node. What's the problem here? Because it's RC new and not RC clone. Okay, some more borrow checker fights, and yes, this now actually works. Okay, so what have we done here? Let's extend our test to see. Again, we kind of like get this addition, and starting from addition, we can actually like let's navigate from this addition to this one. That means that we should start with addition. Look at the children. No. Let's refactor this to return the iterator. Because we seem to always need it. No, that one was correct, and I believe here was one instance where we needed it. Yes, so we can remove this iter. Okay, so let's try and navigate to that second one. We start with addition, and then we take children, and then we take 0, first, second, third, fourth child. Into node wrap. And let's implement here generic conversion method. This will be some node, and else it will be none. And let's do the same for token. So here we will return none, and here we will return some token. Null 2, and then let's 1, 2 would be L2 children next unwrap into token unwrap. Okay, let's see. If we get this right. Because we also need to actually, yeah, let's keep this even simpler. And keep this cloned. So then we should remove this, and then the red node. We actually don't need these arcs anymore. And that probably needs something like this. Okay, and actually that worked. So now we see that this is the second one. The problem is though, like there is no way we can go to the parent node here. It's like doesn't work, does not compute. So let's redo this using the Red API. First we create a red node. Actually, let's just copy paste this because I think the code will be exactly identical. New, and let's actually call it new root because it's important that this creates new root node. And we'll start with addition. Okay, we also need to implement a batch of displays to make this work, and displays should be copy pasted from green. Okay, yeah, that's one. Red, okay, red node data. And actually here we will just delegate to green node. And the same for red token. And the same for red element. Actually, can we... Interesting, actually, that's funny. No, it's okay. Like, yeah, we cannot write an inherit impl for an arc, but this impl is like I was confused that I thought that this is forbidden by coherence, but it obviously isn't. And here we actually need to set the image self and delegate manually Okay. So yes, uh, that's it. Now with this Red API, we actually can navigate to this second one and then navigate to its parent, and then we can get back to the original addition. Yeah, and it all just works. And also, when we are printing this one, we can print its offset. And we'll see that like the offset is 8, just as we wanted to. So although the green node for this one is the same as for the first one, its offset is 8. And yeah, that's roughly how you can represent syntax trees in, well, yeah, I guess we should also implement this changing of nodes here. I wonder if I have Steam for it. Yeah, I have some T left, so I have Steam for it. So let's give a summary and then continue coding. Okay, so this is in a nutshell how you can have both immutable, purely functional syntax trees, and also parent links and absolute offsets. And a cool thing here is that if you look at the implementation of the operations of the like red nodes, complexity is constant. When we treat children, like we do some code here, but it's not like we need to do more than a constant amount of operation. Basically, all we need to do here is to allocate a new green node. Like for each step where we iterate, we need to allocate a new red node, and we need to increment a reference count on the green node, and that's it. There is like no deep cloning of any kind. And this gives you pretty efficient and pretty convenient traversals for green syntax node. Finally, in the green node, we had this ReplaceChild API, which returned the same green node. So now with the red nodes, we can actually use this API to modify some node deeply in the tree. And that's actually would be like complicated. I wonder if I will be able to implement this without bugs, but let me try. And let's say that we have replaced child, and let's say that the new child is actually, yeah, let's say for simplicity that we will be replacing the child with a green node. So like semantically, red node means like a specific kind of like node with identity within a tree, and a green node is just a subtree. So we will be replacing a specific child of a red node with a green subtree. And what we will get back in return is that we will get back a new root node. So it won't be the node which points to the same element, it would be a node which points to the root of the new modified tree. So yeah, we'll have red node. And again, this will need accept reference. It's interesting. It like when I originally designed Rowan, this syntax wasn't stable. You wouldn't be able to write methods for args. But now that it's stable, I wonder if it has repercussions for the Rowan API. Maybe we could simplify stuff using this. Anyway, So first we say that like the new green node is self green replace child index new child. Actually, we don't need this assertion because it will be triggered here. But now we want to replace ourselves with this new green node. So let's say self replace ourselves with new green node. Yes, sadly, no create from usage yet. Not sure if we need RC here or not. And what we want here is that we want to do a recursive check. We want to check if self parent is none, then we should just return new root with the specific green node. Otherwise, I want to replace child in the parent. And here I need to know my index. We cannot just, well, we kind of like, I guess we can infer my index from like the green nodes using like some binary search or stuff like that. But it's better to just say index in parent. And then this we can then enumerate. One more thing, well, two more things to fix. First of all, you note that when I've called field struct fields, it inserted index and parent the last. But I actually want to insert it to the same position where it is in a struct declaration, where it is next to parent. So there is like this separate order fields as is, but really we shouldn't be inserting it at the end in the first place. And second, you see that it uses like empty tuple here, but we already have index and parent field of a variable of the appropriate site in scope, so it should generate code like this. So self, and that doesn't compile because we also imported some like random things. Okay, this doesn't actually need an explicit lifetime, I think. And replace child. Yeah, it returns green data, but we actually want an RC, so let's wrap this inside an arc. And we also want this to be, we also want this to be an element, so we need to call into here, like, that's slightly confusing. Basically, new green is green node, but replace child allows replace a node with either child or token, so we need to convert that into node on element. Okay, nice. So let's now look at this. So let's stop at this mule2. which points to this multiplication. And let's now actually replace 1 with 3. For that, we create a new token. And then we say let new root equals mule2 replace child, and 2 and 1 was, well, 1 was the first child. So we replace the first child, 0 child, with 3 into. And let's print new root. Okay, yeah, perfect. I'm excited that this works. It's surprising. Live coding is hard. But anyway, so yes, we successfully took our immutable tree and modified it in the usual immutable sense by returning a fresh copy of a tree with a subtree substituted. So we replaced this one with this 3, and this one is the same. And this works correctly despite the fact that this one and this one actually structurally share the same node. I guess that's it. Next time we will be looking how horrible it is when you actually try to make something prematurely optimized out of this data structure. No, I'm joking. I guess next time we'll be still looking at this code, and we will try to add an ST layer on top, because like the biggest drawback here is that the syntax tree is like completely untyped, so it's very hard to work with it. Like you want to say something like struct fields, struct.name, and stuff like this. But in this API, you only have children, which returns you an iterator, and you have to like manually look for nth child or for a child with a specific kind. So we will make it better next time. And for now, I guess that's it. Thank you for listening.